And now we move on to the examples part of our discussion on quantum mechanics. The examples part is divided into two parts. In this video, we'll have part 1 and then we'll have part 2 in the next video. So let's have example number 1. Calculate the de Broglie wavelength of a 0.65 kilogram basketball thrown at a speed of 10 meters per second. A non-relativistic electron with a kinetic energy of 1 electron volt and a relativistic electron with a kinetic energy of 108 kilo electron volts. So we have the basketball. Mass of the basketball, mass of the ball is 0.65 kilograms. Speed of the ball, V ball is 10 meters per second. Whereas you have an electron, mass of the electron is given by 9.109 times 10 to the negative 31 kilogram. The problem also gives us the kinetic energy of the non-relativistic electron, 1 electron volt. That's equivalent to 1.602 times 10 to the negative 19 joules. The relativistic electron has a kinetic energy of 108 kilo electron volts. That's equivalent to 1.73016 times 10 to the negative 14 power joules. So this problem is divided into three parts, A, B, and part C. So let's have part A first. The de Broglie wavelength of a 0.65 kilogram basketball thrown at a speed of 10 meters per second. When we say non-relativistic, in terms of speed, the speed, when you compare it to the speed of light, the speed of the object is very much smaller. You will have a smaller than c, you will have a non-relativistic case. For there to be a relativistic, for the system to be relativistic, the speed involved should be at least close to or equal to the speed of light c. Of course, i- going going back to the topic of Einstein's special theory of relativity, it will be shown that no object with mass is able to attain the speed of light c. So, for a relativistic system, the speed should be at least close to the speed of light c. V ball is 10 meters per second. C, you will recall, is 3 times 10 to the 8 power meters per second. So V ball is very much smaller than C. You have a non-relativistic case. Non-relativistic case, you go back to classical physics. Momentum of momentum of an object in classical physics is simply given by P is equal to mv. So momentum of the ball times mass of the ball times speed of is equal to mass of the ball times speed of the ball. That will give us 6.5 kilograms meters per second. So 0.65 times 10. The de Broglie wavelength is given by P is equal to h over lambda. Rearranging, we have lambda is equal to h over P. H is a constant, so we know the value of that. And we have just calculated P ball, 6.5 kilograms meters per second. We are able to calculate the de Broglie wavelength of the basketball. 1.019 times 10 to the negative 34 meters. Now, for letter B, non-relativistic electron. Non-relativistic, so we go back to classical physics, kinetic energy, classical physics is given by 1 half mv squared. So kinetic energy of the electron is 1 half times mass of the electron times square of the speed of the electron. Isolating speed, we are able to get 593,076.755 meters per second. So the electron is quite fast, but still, when you compare it to the speed of light, still very much smaller than the speed of light. So indeed, this is non-relativistic case. Non-relativistic momentum is given by mass times momentum. De Broglie wavelength, P is just equal to h over, for a de Broglie wave rather, P is just equal to h over lambda. So, mv is equal to h over lambda, isolating lambda. We are able to calculate the de Broglie wavelength of the non-relativistic electron, 1.227 times 10 to the negative 9 meter, or 1.227 nanometers. And lastly, we have the relativistic electron. For relativistic electron, you need to go back to your special relativity. So please consider that as a reading assignment. Please review your, at the very least, the basic equations of your special theory of relativity. One equation from our special theory of relativity is given by E is equal to KE plus E naught, where E naught is the rest energy of the object, energy of the object when the object is at rest, and it's just given by the rest mass of the object times C squared. Rest mass is mass of the object when it is at rest. We know the mass of the object, electron, ME. We know the value of C, and KE is also given. We are able to calculate the total energy E2. The total energy of the object is 9.92826 times 10 to the negative 14 joules. Another equation from our theory of special relativity is E squared is equal to P squared, C squared plus M naught squared, C to the fourth power. Knowing that P, for a de Broglie wave, knowing that P is equal to H over lambda, we need to isolate P in this equation. Once we isolate P, we already know all the values. We calculated E, total energy E2. We know the mass of the electron. We know the speed of light in vacuum. We are able to calculate the momentum of the object, the electron. 1.866711399 times 10 to the negative 22 kilogram meter per second. And applying now our equation for a de Broglie wave, P is equal to H over lambda, lambda is equal to H over P. Knowing P, knowing the momentum, we are able to calculate the de Broglie wavelength of the relativistic electron, 3.450 times 10 to the negative 12 meters. So again, it will pay for you to review your special theory of relativity. Be familiar with the basic equations that you get from your special theory of relativity. Next, we have the following example. What is the energy of a photon whose momentum is 3 times 10 to the negative 24 kilogram meter per second? A photon, particle of light, is massless but it has momentum. Photon is a massless particle. It can exist for as long as it has energy and momentum. So P is equal to E over C. Isolating E is equal to PC, knowing P is 3 times 10 to the negative 24 power rather. So this should be negative 24 kilogram meters per second. PC will give you 9 times 10 to the negative 16 joules. E is equal to 9 times 10 to the negative 16 joules, or 5.618 times 10 to the third power electron volt. So again, slight correction. This should be times 10 to the negative 24. Next, we have the following example. Example number 3. A ball is constrained to move along a line inside a tube of length L. The ball is equally likely to be found anywhere in the tube at some time t. What is the probability of finding the ball in the left half of the tube at that time? So the ball is equally likely to be found anywhere in the tube. So say if you divide the tube into 10 parts, in one part, the likelihood of finding the particle at one part is 10%. The 1 over 10 or 10%. If you divide the tube into two, left half and right half, the likelihood of finding the ball in one half, in let's say the left half, logically will be 50%. Mathematically, we can show this using Schrodinger's, not Schrodinger's equation, but using the concept of the wave function. The ball is equally likely to be found anywhere inside the ball. As such, we can write down the wave function capital psi of xt as shown. Psi of xt is 0 for x less than 0. And for x greater than 0, the wave function is also 0. We are only able to find the ball inside the tube, so the psi of the ball, the wave function of the ball from from 0 to L is constant. Constant meaning equally likely to be found anywhere in the tube. Using now our equation for the probability of finding the particle, if we set the range from negative infinite to infinite, we find the probability of finding the ball 100%. But 0 plus 100% plus 0, 100%. So P is equal to 1. The same goes if we remove less than 0 and greater than 0 for x and just focus on the distance 0 from 0 to L. The probability of finding the object is also equal to 1 or 100%. Since c is constant, we can take it out of the integration. We are just integrating dx. Integral of dx is x from 0 to L. That will give you c squared L is equal to 1. Meaning, c is just equal to square root of 1 over L. Now that we know the value for the constant c, let's now take a look at the probability of finding the ball in the left half of the tube. So from 0 to L over 2, left half of the tube. So again, probability equation, probability density times dx, integral from 0 to L over 2. Knowing the constant c, we are able to calculate the probability. So psi of the probability density, psi is just equal to c, therefore square of psi rather is just square of c. square of c is 1 over L. So we are integrating 1 over L dx from 0 to L over 2. 1 over L constant. We can take it outside the integration. We are just integrating dx from 0 to L. That will give us 1 over L times L over 2. Cancel out L, leaving us with 0.5. The probability of finding the particle in the left side of the tube is 0.5 or 50%. So that's it for now. In the next video, as mentioned, we'll cover the second part of the examples in our discussion of quantum mechanics. So thank you for watching.